I hope you all took a look at the video on colligative properties. We are going to focus in our problem solving. That's what this video is about, one of the first of the colligative property problems, which is on our sheet, our current sheet that we've been working through, problem number 4. And then we'll have a video on problem number 5. Okay, so let's dive in. Colligative properties, we all have seen the video, so we know they have to do with vapor pressure change, boiling point elevation, and freezing point depression. The boiling point elevation and freezing point depression are the ones that we are going to focus on in this class. So let's dive in. Bottom line is, colligative properties, what that means is you have these boiling point elevation, which means like for example, water will boil at a higher temperature if you have something mixed in with that, if you have something in solution. Water will freeze at a lower temperature if you have something mixed in with that, something in solution. It doesn't matter what it is in solution. It could be a salt, all right? It could be a sugar, it could be sucrose, it could be glucose, it could be sodium chloride, it could be potassium nitrate, it could be any number of things which dissolve in water. But if they dissolve in water, now you have particles in the water, and those particles get in the way. They don't allow the boiling bubbly things to come out. They don't allow the crystals to form in the solutions because they just get in the way, and you need colder temperature or higher temperature to achieve the freezing or the boiling. All right, that is a real summation of colligative properties. Okay, so let's dive in. Let's do a problem with colligative properties. If you go to the equation sheet in Essential Documents and you have that, you will see that there are some equations that look like this. Change in freezing temperature, is equal to K sub F. That means K is quite often used for a constant, and this is a freezing point depression constant, F for the freezing, times a little m, sideways italicized, molality. Okay, that's going to be molality. Remember earlier on we did a little discussion of what's the advantage of molality over molarity, and what's the advantage of molarity over molality. Molarity is easy. It's easy to make solutions. Molality is good when you're dealing with extreme temperatures, boiling or freezing. In that case, we use molality with boiling point depression, boiling point elevation, freezing point depression, because the volume doesn't change. You see, the volume doesn't change. This doesn't have anything to do with volume. This has to do with mass. Remember? You remember. Yeah, so we use molality. Okay, so this is going to be a constant, and if we were talking about elevating boiling point, we would have the same equation, except we'd be using little b's here for boiling. And there are these constants for boiling and freezing, and of course, any chemistry books don't have a table of these, or they might have them in the appendix. Okay, you'd find them in the appendix. You're not going to find them in the stomach or the liver. You'll find them in the appendix. It's anatomy. It's funny. Okay. You might find them in the appendix in the back of the book. All right, so you will find these. You can always find. Now the thing is that we're going to really focus on water solutions. I do have a problem on here. The second problem in colligative properties, problem 5, does not deal with water. So I did want to demonstrate that it's not just water solutions all the time, but it usually is. So we'll do a problem with water and not with water. I believe it's benzene that we're going to use in that second of the colligative problems. Okay, let's dive in. So we have water has a K value for freezing, and you'll get used to it, I hope. I hope you will. We'll use it in our problems. We'll use it in the lab that we're going to be doing for this week, and use it in the problems in the book quite often. And that's going to be a 1.86. 1.86 degrees Celsius per little m. Now what that means, the change, there's a constant value, a change in freezing point of 1.86 degrees per mol of solution. That's what that means. Now the KB, this is the boiling point constant, it's not the same, they're different, is 0.52 for water, degrees Celsius per mol. So if we take a look at this, we can actually see that the freezing point K value is about a little bit more than 3 times that of the K for the B, for the boiling. What does that mean? That means that these colligative properties, these particles that you throw into water, are going to be more effective at preventing the freezing than they are at preventing the boiling. They will prevent boiling from happening at 100 if you throw stuff in there, but they'll really do a number on the freezing point of water if you throw stuff into water. Water won't freeze at 0 degrees Celsius or 32 degrees Fahrenheit if you start throwing sugar in it or salt, aka salt on the roads, right? We'll talk about that. Why do you put salt on the roads? What does it do? Okay. So, all right, without further ado, let's get to this problem. Problem 4. Problem 4 says ethylene glycol. All right, big E, big G is how you abbreviate that. Now, we all know what that is, right? We all know ethylene glycol is the chemical name for antifreeze. Antifreeze. You put this into your radiator of your automobile so your radiator won't freeze, hence antifreeze. So it does the job of not allowing the water that's in your radiator to freeze at normal temperature, being 0 degrees, freezing point of water. It depresses freezing point depression. It depresses the freezing point of the water, so your water in the radiator doesn't freeze. If that happens, if the water in your radiator froze, it'd be a bad day because it's going to be quite an expensive repair if that radiator ruptures. Okay, that'd be bad. So you could actually get away without putting antifreeze in your water if you lived along the equator in your sea level. Or maybe if you live in South Florida, in Miami, you might be able to get away with it and not worry about the water freezing because the temperature doesn't get to 0 degrees. You know, it'd be freaky if it did. So you can get away with it there. But here in New Hampshire, nine. You cannot get away with, in the wintertime, just having water in your radiator. And water is a great coolant. That's why we put water in the radiator as part of the cooling system of your automobile. It does a great job with distributing heat to the environment that's generated in the engine. You gotta have it or your engine will overheat. And you can just put water in the radiator. You can. But you're not gonna be very happy when, you know, October, November, December rolls around. Bad things are going to happen unless you put some antifreeze in there. So I'm just giving you a little bit of application to the chemistry and why I selected this particular problem. It's very applicable to living in New Hampshire. The other thing too is it allows boiling point elevation so the water won't boil as easily when it's in your heating system. But the other thing you have also is the water that's in the cooling system, I said heating system, cooling system of your automobile is also under a lot of pressure, and that has an effect on keeping the water as liquid as well. So the combination of pressure in that radiator and with antifreeze in it helps it stay as liquid water, okay, and do its job. I'm just keep bantering here along, but this is important stuff. This is important stuff, okay? So, all right, now you've fallen asleep, wake up. Here we go. We're going to solve this problem. All right, so ethylene glycol is a common automobile antifreeze, okay? Got that. Calculate the freezing point of a solution containing 651 grams of the substance and 2,505 grams of water. What would the boiling point of this solution be? So it wants two things. It wants to calculate the freezing point of the solution, and then we'll calculate the boiling point of the solution. And I do give you, because you've had a rough day, okay? No, you've had a rough day, so you relax. Instead of you adding up all of these, all this stuff here, I've done it for you. Okay, I've done it for you. The molar mass of ethylene glycol is 62. It's 60.0. I'm missing 62 in my calculation. So that all together is equal to 62. I've done that for you. So you sit back, relax, eat your popcorn, drink your root beer, okay, and watch the show. Okay, from the table, and that's table 12.2 out of the book that we use for the class, the chain chemistry. We use that one. So it's in there. Any chemistry book, you'll find this. You'll see the 1.86 degrees Celsius per molar. There you go. Degrees Celsius per molar. Sorry, on the board for you. Again, I'm here for you. I put these down for you so you don't have to look them up. Okay? Again, you relax, chill. And we also have that one down for you. So we want to figure out both the freezing point of this solution and the boiling point of the solution. We're going to actually use both of these equations. I mean, they're very similar. The only difference is that we put in a different K value. That's it. So we need to figure out the change in the freezing temperature to get the answer to this question and the change in the boiling temperature. Well, what do you mean? How come you want to get the change? It asks us for the freezing point of the solution and the boiling point. Now, I don't see that in the equation, so how are we going to figure that out? Well, if we get the change in the freezing temperature and the change in the boiling temperature, we know that water should boil and freeze at. We know that. You know water should boil at 100 degrees Celsius. And it should freeze at 0. You know that. So if we get a change, we calculate the change in the freezing temperature of like -10, then we know, or the change of 10, then we know that the solution would freeze at -10 because 0, normal, minus the change, 10 would be -10. And we know that if we get a change in the boiling of 5, then water should boil at 100 at sea level. And if it changes by 5, it's going to elevate by 5 degrees, 105. See? Say it's not so bad. All right, so let's go ahead and figure out the freezing temperature change first. Okay, so delta TF is going to be equal to, for water's freezing, we put 1.86. And then we need to figure out the molality. Oh, we weren't given the molality. Oh, we got to figure it out. No. Yeah, come on, this isn't going to be hard. It isn't. I know. You said that about problem number 2 and number 3. No, I didn't. I said those were going to be hard. Okay, yeah, maybe you did. Thank you. Okay, now this is going to be a straightforward molality calculation. And we know that molality is equal to moles of the solute, yes. And what's the solute here? What's the solute? We're taking ethylene glycol, antifreeze, and we're adding it to water. So the ethylene glycol is the solute. So the moles of Eg divided by kilograms of solvent, which is water. Okay, it's water. Okay, well, there's our setup. So we have to figure out how many moles of the ethylene glycol we have. Okay, let's go ahead and figure that out. We remember that we want to get moles, so we have grams of the ethylene glycol. 651 grams of the ethylene glycol were added. So 651 grams of ethylene glycol, multiply, divide, grams of ethylene glycol. And we all remember that when we go from grams to moles, we put a 1 next to the mole. And we're going to look up the mass of ethylene glycol. But I've done it for you. You relax. It's 62. All right? We already got that for you. So 62. So 651 divided by 62. That will give us the number of moles. Okay, it's going to go in there a bunch of times, like 10 point something it looks like. Let's see. 651 divided by 62. Come on, kids, calculate at home. Calculate at home. All right, we get 10.5 moles of the ethylene glycol. That goes here. Okay, that goes here. So molality equals 10.5. That's the moles on top. Kilograms of the water? Well, that's easy. We have how many grams of water? We had 2505 grams. Remember how to get grams and kilograms? 3 places to the left, everything you own, 3 places to the left. Well, I got some skills, huh? I got skills. So move it 3 places to the left, 2.505. 2.505. That'll give me my molality. I like saying it that way. 10.5 divided by 2.505. Boom! So the molality is 4.19. 4.19. That 4.19, all right, is the molality, which I am now going to put here. 4.19, molality. So molality here, that's the unit here would be M. This is degrees C per M. The M's cancel, we get degrees C. That'll be our change in the freezing temperature. So that times 1.86, 796, so we're going to make it 7.8. So 7.8 degrees Celsius is my change in the freezing temperature. So the question was, what's the freezing temperature? Well, you know that water normally freezes at 0 degrees. So it changed by 7.8. It's a depression change, so 0 minus 7.8 is negative 7.8. So now we have our answer for the freezing point. This is the freezing point of the solution of the ethylene glycol in water, and that would be negative 7.8 degrees Celsius. Okay, that's one of our answers. The other answer is going to be, what's the boiling temperature now of this solution? So I'm going to use the same equation. I got to remember that 4.19 because the molality is still the same. The molality of the solution doesn't change. We calculated that already. So this should be a quick calculation. The only thing I'm going to do is these become B's, the boiling point temperature change times the boiling point constant, couldn't think of the word, that becomes what I put in to the equation. So I don't use 1.86 for the boiling, I use 0.52. So 0.52 multiplied by 4.19, it's still the same concentration of the solution. So I multiply those two together, and 0.52 times 4.19 is 2.18. 2.18 degrees Celsius. So that's the change in, that should be a B. Did you catch that? Did you catch that? That should be a B. This is the change in the boiling temperature. Now we know water with nothing in it will boil at 100 degrees Celsius at sea level. And so we're doing our calculations here in, in New Hampshire. We're not very high above sea level in Manchester, so we're calling it sea level. So we would be boiling, our water should boil at 102.18. We add this to 100, the normal, because it's an elevation, we add it as opposed to subtracting with the depression. So add it, and we get 102.18 degrees Celsius. And those should be our two answers. And I put the answers down here for you, and we'll check them. 7.79, I made it 7.8 and 102.18. And, actually, I should have put down here, I said what were the boiling point solution? Actually, that answer is actually incorrect. What's wrong with that? 2.2. That's the elevation. We should have added 100 degrees to that. So that's a typo on there. I got to change that. So it should be 102. And you can make that 0.2. Okay, so 102.2. So that is a quick, relatively straightforward calculation using our colligative properties, boiling point elevation, freezing point depression, and our two equations, which are really kind of one equation. You just change the subscripts. Pretty straightforward, that one. I just want to say one thing about the ethylene glycol. Typically in New Hampshire, you put a 50-50 mix. This is not, if somebody was doing this, either your radiator is probably going to freeze on those cold January days. That's not going to get you through the winter, not in New Hampshire. Usually go 50-50. When I used to do my own, back in the day, when I had time and, I was one of those young, let's do our own car repair work stuff. Yeah, I used to change the radiator fluid in water in the radiator on my own. Occasionally I got to do that. And, I get a container of antifreeze Prestone. I remember back in the day it was Prestone. And you'd look on the back of it and it would have a little chart for where you lived in the U.S. And I said Northeast United States, it wanted a 50-50 mixture. So I'd add 50% water and 50%. So it was a 50-50 mixture. And that will cause this freezing point to go down a lot farther, and you'd be good to go. All right. Okay, that is problem number 4. Problem number 5 is going to be muy importante, grande. Yes, not just for your first academic adventure, because I'll have a problem like this, but also for the lab. We're going to use it. We're going to use this boiling point elevation and freezing point depression to determine the molecular formula for a compound. Whoa, what? How are you going to get a molecular formula out of that? Stay tuned, people.